Okay, I'm going to talk on the practical side of verification and diagnostics, looking at aircraft data in particular, and mainly Mode S, which is very high resolution data. Okay. Right. So I'm going to show you two examples on observation minus analysis maps, a bit about Mode S introduction and what the problem was, improved thinning and results, and a summary. And the sort of, in terms of results, the bottom line is that there was a problem using Mode S with the old thinning. Not using Mode S at all was better than that, but using Mode S with more severe thinning is better than either of those two. And the data is provided by the EMADDC team in the Netherlands. Now, this is not Mode S, but it's a different aircraft problem. From December last year, and I looked at the map on the left, which is standard deviation of O minus A for wind speed at about 200 hectopascals. And I thought, what's that red blob in the tropical West Pacific? And the sort of general feature is that the O minus A magnitude is relatively flat for used data. It's much flatter than the O minus B plot. So if you looked at O minus B, that blob didn't stand out nearly so much. And I looked at the Chinese AMDAR in particular, and the problem was there. And it turned out to be wrong sign of latitude in the Boeing 787 data. But that's just to show you the use of this diagnostic on the right occasion. Going back a bit further, early September 2022, I saw a version of this plot for Mode S data. It's the same field, standard deviation of O minus A, and I was unhappy seeing the maximum in Central Europe. I expected to be flatter. Now the bits around the edges are almost certainly due to small sample size. I'm not worried about those. But the bit in the middle, I had two questions. Is it linked to very high data density there? And is it a sign of ill conditioning? And it turned out the answer was yes to both of those questions. And this is just a plot of the data for 30 minutes. And the bottom line is that where we've got Mode S receivers, it really dominates the aircraft and to some extent the upper air data coverage. We started using Mode S in summer 2020 during the pandemic when aircraft numbers were depressed, and we put it into operations quicker than planned then because of the pandemic. And we just put it in winds only, essentially as AMDAR data, using all the same parameters. And then the short haul aviation recovered, and we were using 2 to 3 times as many Mode S data over Europe as we were doing all other aircraft data globally. And I noticed we had a problem. So we took it out in November 22, and it was reintroduced in November 23, thinning by box rather than by track. And I'm also thinning the other aircraft data more than we did before. And a check taking out Mode S confirmed that certainly in the Northern Hemisphere, it was making things worse. And yeah, quick and dirty time thinning didn't help, or didn't help enough. And diagnostics. I mean, for large samples and a good data assimilation, we must have the RMS fit to analysis less than the RMS fit to the background. Now, that could be 1% better, or it could be 50% better. It depends on things like data density and the relative errors. And the other, a bit of explanation on the plots I'm about to show. The operational high resolution system has 4 outer loops compared to 3 in research experiments. So the operational system might suffer less from convergence problems, and that does seem to be the case. So this is left-hand side, there's radius on plots. Right-hand side, there's Mode S plots. The blue lines are O minus B. This is all winds profiles. And the red lines are O minus A. So for looking at the top plots on the left for the radiusons, the fit, O minus A fit in the upper troposphere and lower stratosphere was worse than the O minus B fit. That's a problem. And we see similar for Mode S. Jumping ahead to the new plots in the bottom right, the lines are the right way round. The analysis fits the data better than the background. And the right hand side next to that for Mode S shows N-wind used per day, and in most of the troposphere we've maybe halved the data used, but in the cruise levels it's much reduced. With the revised thinning compared to no Mode S, this is the T+12 fit to European Radisson data, and we see benefits of 6%, in some cases more, in the upper troposphere. That's for the winds, the solid lines. For the temperature, the dashed line, it's about half that, but it's still a worthwhile improvement. And these are big changes in the upper troposphere, and it's much larger than seen in limited area models. because we've got wider data coverage.
You have
And
3 minutes left.
okay, thank you. And this is what we call a scorecard for this work. And the top half is verification against own analysis, and the bottom half is verification against observations. The right-hand columns, there's Europe and there's North America. And I showed you Europe looks very good against radiosondes, and it looks awful against own analysis. North America, we've reduced the numbers of AMDARs used, and that looks very good against own analysis. And the bottom line here is that the radiosondes used for verification here can be considered independent. Own analysis can't, and this is a problem for short range verification against own analysis. So the summary is that MODES was introduced quickly in 2020 with benefit. By 2022, the increased data density was making 40 VAR ill-conditioned over Central Europe, more iterations and cost, and worse forecasts. So we switched off the use of MODES data and tested box thinning, and reintroduced that in November 2023. And with the new thinning, it works very well over Europe. We see a big improvement against radiosonde wind in the upper troposphere, and it makes the system more robust. It's a similar cost to not using MODES. But diagnostics, the points I want to make are that O-A maps are useful, and also comparing O-A with O-B is a useful tool. Verification, you need to look at both against analyses and observations, and I think many of you will know this, but you can have a misleading signal against own analysis at short range, and there's a paper by Hotter et al. About this last year. Okay, thank you.
Thanks a lot. Maybe while there's one question just currently written to the UPad, I would have a short question to you. So on slide 6, you mentioned the new thinning, and you also mentioned that you introduced less thinning for Arab data and so on. And I'm not sure I've understood this this comment. Do you only include less thinning over the ocean, or do you have separate thinning ideas for ocean and land, or is it everywhere the same for Arab and Tiander and stuff like that?
Okay, for a lot of the time, I was doing the same thinning everywhere. And results in the southern hemisphere weren't quite as good as I wanted. And so I changed it so that there was less thinning for certain aircraft categories. ADSC, AirRep and TAMDAR, which are mainly oceanic. And that is rather roughly a way of looking at the data density, but not explicitly. Thanks.
Okay, thanks for the clarification. Then there's a comment by Talleyrand, and he's saying, okay, there's theoretically a one-to-one correspondence between ops minus B and ops minus A. Diagnostics performed on both sets are numerically different, but fundamentally equivalent. Yeah, I think it's more of a comment. And we have another question by Daisuke Hotta. Very informative talk. Thank you. Does neglect of off-diagonal R also count for degradation when mod S observations are too dense?
It might be an issue. I've been having an ongoing discussion about this. I mean, well, I think we're probably thinning enough that we can neglect it. There is a question of whether we get better results by thinning less, but representing correlated errors. The problem is implementing that in practice. I mean, there are ideas, but they sound quite expensive. So it's a possible area of future work. Yes, thanks.
Okay, thanks.
Yeah.
Then I